Welcome to This Explainer. Today, we're investigating an incredibly fascinating new diagnostic tool that uncovers exactly why today's smartest AI agents suddenly just fail at complex computer tasks. Have you ever watched an AI agent try to book a flight or maybe organize files on a desktop, only to completely lose its mind the second a random notification pops up? It's wild, right? Well, today we are breaking down a brand new research paper that reveals the precise mechanical blind spot causing these failures. Here's our roadmap for today. First, we'll look at the AI agent blind spot. Then we're introducing desktop delta bench. After that, we'll move into the interrogation, check out the verdict, and finally, wrap up with the missing diagnostic layer.
All right, let's jump right into section 1, the AI agent blind spot.
To truly understand the problem here, we first need to look at how we're actually grading AI on computer-used tasks today. Because right now, quite frankly, our grading system has a massive loophole. The crucial thing to understand is that current end-to-end benchmarks, which basically test if an agent can successfully complete a final task in a live virtual machine, well, they tell us if an agent finished the job, but they completely fail to tell us how it got there. They're entirely missing the intermediate reasoning logic. It's like a student getting the right answer on a math test without showing their work. Did the AI actually understand the screen transitions along the way, or did it just get lucky? We desperately need what we call transition-level benchmarks to score those step-by-step graphical user interface changes and actually isolate its visual reasoning. This exact gap in the industry becomes glaringly obvious when you map out existing diagnostic tools against the environments they test. Looking at how things currently stack up, popular benchmarks like ScreenSpot Pro and OS World are at the top of the pack. OS World, for instance, tests across 9 different applications and scores live agents on their final outcomes. But if you scan over to look at transition-level evaluation, there is a distinct, undeniable lack of step-by-step diagnosis. Almost across the board, you just see red X's or notes saying the diagnosis is merely implicit. Now, a web-based tool called EvoGUI does offer transition-level scoring for browser tasks, but because it's strictly limited to the web, there's still a massive blind spot for native desktop environments. Up until now, there was absolutely no tool that systematically tested step-by-step visual reasoning in a desktop Linux environment. So that brings us to section 2, introducing desktop delta bench. This is the incredibly clever solution presented by the researchers. It's called Desktop Delta Bench, or DDB for short. It's a brand new offline benchmark containing over 2,000 human-verified instances, all recorded on Linux. And the architecture here maps out exactly how they set a trap for these AI models. The whole workflow kicks off by recording real human workflows, think using spreadsheets or file managers, at 10 frames per second. This rigorously captures and aligns synchronized keyboard and mouse events to create a totally flawless timeline of actions. Then, the benchmark chops this highly detailed data into 2 core tests for the AI. The first is the temporal ordering task. Here, the AI is handed 3 screenshots in a deliberately shuffled order. Its job? Calculate the exact correct chronological timeline, the gold answer, to prove it actually understands cause and effect on the screen. The second task is single action reconstruction. The AI gets a before and after frame and has to output the specific coordinate data and the action family, meaning was it a left click, a scroll, or a keystroke, that bridges those 2 frames together. Now, a massive and brilliantly devious part of this benchmark tests for something called context poisoning. So what is that? Well, it's what happens when an AI gets confused by a pop-up, a stale UI window, or maybe a visually similar but completely incorrect file, and then inadvertently carries that bad data forward into its reasoning. DDB tests this by actively sneaking a decoy screenshot from a totally different recording into that temporal ordering test we just talked about. They're effectively setting a trap just to see if the AI will confidently fall for the trick and try to fit a fake timeline into the real one. It's a fantastic stress test. Let's move right into section 3, the interrogation, tasks 1 and 2. Let's see how this all builds into the specific ways DDB interrogates these models across 50 unique task domains. The distribution data for the temporal ordering task is mapped out across 463 testing triples, and it's highly revealing. The largest chunk, about 36.5%, aggressively tests for context-aware control. Following closely behind that, 34.6% of the data tests source and item tracking, and 28.9% tests state verification. But if you drill down into the granular details, you see these fascinating subcategories, like hidden state analysis, source authority checks, and recovery and rerouting scenarios. The benchmark isn't messing around. It's testing deep, complex visual comprehension. Now, pivoting over to the single-action reconstruction methodology, which spans 1,550 pairs, you'll notice a massive portion dominates the data. 70.8% of the actions are clicks, followed by drags at just 11.1%. And here's a key detail. The researchers explicitly chose not to artificially balance these numbers. They kept this heavy skew toward clicks because it perfectly reflects the actual natural distribution of real-world daily office workflows. Training an AI on artificial, perfectly balanced academic data just isn't going to help it navigate a real desktop. The researchers also implemented a fiercely rigorous mathematical framework to score the AI's performance, ensuring absolute precision. To pass, the AI must accurately guess the action family, meaning it has to figure out autonomously if an action was, say, a continuous click or scroll, and then it has to extract the exact payload. For text entry, this literally requires an exact Unicode string match. So if a human typed a capital A, the AI must output the precise underlying computer code for that capital A. For mouse movements, spatial tolerance is calculated using diagonal normalized distance. That's just a fancy way of saying the system measures exactly how close the AI's predicted click coordinate is to the actual target pixel relative to the diagonal span of the entire screen. A drag action, that requires plotting both the exact starting coordinate and the exact ending coordinate. Basically, there is zero room for hallucination here. The benchmark demands microscopic spatial accuracy. Which brings us to Section 4, the verdict. Benchmarking models. So the mathematical trap is completely set. The grading rubric is established. How did 8 of the leading open and closed source models actually perform? You'd probably assume that multi-billion-dollar frontier models like GPT, Claude, and Gemini would just ace this visual logic test, right? After all, these things can write complex software and pass medical exams. But the data reveals a pretty shocking reality when it comes to understanding graphical user interface transitions. When we look at the accuracy breakdown, it definitively proves that temporal ordering remains completely unsaturated by current AI technology. Looking at the exact match accuracy, with the y-axis tracking the accuracy percentage and the x-axis plotting the different models, the results are wild. In the category for non-decoy exact match, even the absolute best models we have, like Gemini 1.5 Pro and Gemini 1.5 Flash, only hit around 65% accuracy. That's it. The metrics tracking Decoy 1 exact match and pairwise accuracy show similarly staggered, honestly uninspiring performance across the board. But the real kicker is the measurement for decoy identification, which reveals a massive industry-wide variance. Claude 3.5 Sonnet manages a highly impressive 97.1% accuracy at spotting the fake poison screenshots, successfully dodging the trop. But the open source models? They completely plummet on this metric. Across all these rigorous testing parameters, the gap is glaring. Closed-source models outperform open-source models by a staggering average of almost 23 percentage points. But my absolute favorite finding exposes a massive vulnerability that we can lovingly call the lazy AI phenomenon. When presented with screenshots labeled A, B, and C, many open-source models, specifically GLM4V and Minimax-01, fail 37 to 45% of the time for one ridiculous reason. They simply blindly echo the A, B, C presentation order they were handed. Instead of doing the hard computational work to actually analyze the visual chronology and realize, oh wait, screenshot C clearly happened before screenshot A, they just lazily repeat the input sequence. By contrast, top-tier closed-source models successfully suppress this bias. But think about it. Without a step-level diagnostic tool forcing these models to prove their visual math, this massive structural laziness would have gone completely unnoticed in standard pass-fail testing. Let's move into our final section, the missing diagnostic layer. Let's wrap up by looking at what these profound blind spots actually mean for the future of computer use agents, and how developers can use this data moving forward. The researchers perfectly encapsulate their goal here. They absolutely aren't saying end-to-end benchmarks are bad. Rather, they thoughtfully position this tool as the ultimate diagnostic bridge. If an AI suddenly fails a complex end-to-end task in a live environment, Desktop Delta Bench acts as the microscope developers can pull out to find out exactly which visual transition confused it. To summarize the core takeaways from all this data, we now fundamentally know that inferring which action occurred is often much harder for AI than simply localizing it on a screen. For example, standard clicks are relatively easy for AI to understand, scoring a massive 0.96 F1 score, which is a metric that powerfully combines precision and recall to measure overall accuracy. But drags? They drop significantly to a 0.76 F1 score. Why? Because mechanically, a click is just a single coordinate point. A drag, however, is a complex, continuous action. The AI must plot a starting point, recognize that a state is being held, and accurately identify the release endpoint. Spatial reasoning and action recovery remain massive hurdles. We also learned that providing the AI with a text prompt about the task helps it figure out which screenshots belong to the same workflow, but that text instruction provides absolutely zero help in determining the actual chronological order of those images. And all of this leaves us with a critical realization about the bleeding edge of AI development. We are rapidly pushing for autonomous agents that can manage our emails, organize our finances, and execute our daily computing tasks in the background. But if these frontier models still struggle to figure out if a file was saved before or after a window closed, or if they just lazily accept poisoned decoy information as fact, how on earth can we trust them with our most critical, sensitive workflows? It's a fascinating technical challenge, and thanks to the uncompromising rigor of Desktop Delta Bench, it's one we can finally start to measure, understand, and fix.